We would like to welcome our last speaker, Mr. Matthew Smith. He'll be discussing developing a sustainable and performant GPU implementation of plane wave DFT. You have our full attention.
Thank you very much. Hello. Thank you for attending. My name's Matt. I'm a research software engineer at the University of York. And my main work at the university is developing the CASTEP code. Some of you have already mentioned that in the previous talk. I work alongside Ian Tamaris, who's at the University of Cambridge, and also Phil Hasnip, who's one of the core developers of the CASTEP code. He's at the University of York as well. And the previous excellent talks have all been focusing on applications of HPC. All my work is in the development of the actual code, so that's what I'm talking about today, and in particular the GPU port of this of the code CASTEP. And the little logo you can see at the top there, the Excalibur logo, this is advertising essentially. This is why we're here today, representing CASTEP. The Excalibur project is UK funding that's helped us in our research, preparing codes, HPC codes towards exascale, and so that's why we're here today. How do I? Okay, maybe is it that one? Yeah. Okay. So first of all, very briefly, I'll just introduce CASTEP. As I said, it's one of the flagship Excalibur codes, and it's a material modeling suite that's using plane wave pseudopotential DFT. It's been developed over the past 20 years or so, currently stands at about 750,000 lines of code, written in almost exclusively in Fortran 2008. Extensive use of MPI and OpenMP throughout the code. Parallelism's really at the forefront of the code. And the commercial GPU support is being released under the materials modeling umbrella next month or early next year. And when I was preparing this slide, I was thinking about do I need to provide a motivation really for a GPU port for a code? Seeing as though I made an HPC conference, I thought maybe not. But I'll suffice to say here that when we started the project, probably about 7 or 8 years ago, the idea of a GPU port for a DFT code was kind of like a nice thing to have. People were saying, okay, well, it'll speed things up. How fast will it go? So on and so forth. Whereas really in the last year or the last couple of years, the position has changed somewhat, really, where people are now saying, well, simply all of HPC is going towards GPU. We've got GPU-centric machines all across the world at tier 0 and downwards. So the idea of not having a GPU port of your code becomes a problem. So it's really a necessity now rather than something that's nice. And the little graph you can see on the right-hand side, this is just showing you how popular CASTEP is in terms of academic citations and so on. It grows every year. It's all very healthy. Okay, so I'm going to focus on the porting of the code to the GPUs, and really there are 3 cornerstones of the porting strategy that I'm going to use as a framework for this talk: performance, portability, and sustainability. And these 3 cornerstones have a symbiotic relationship. And they're all important to one another. But if I had to prioritize one, it would probably be sustainability. The reason being that without that, you can't really have any interest in the other 2. So I'm going to start with sustainability, and then I'll work my way around this. But hopefully you'll see why it's so important. So what do we mean by sustainability with the code? Well, particularly we're thinking about sustainability with respect to code maintenance and also software development. And our solution to achieve both of these goals was to take a directives-based approach to, take a directives-based approach to porting rather than using a proprietary language such as CUDA. The reason for this is immediately the directive-based approach gives you a unified source code which avoids any forking in the code. This is something that other DFT codes, plane wave DFT codes, have had problems with in the past. They've developed very sophisticated, very performant say, CUDA-based codes. But unfortunately, seen as though by definition they become forks of the main branch, they end up in a dead end and then become orphaned, and they've had to start again. And actually, I've ended up taking directives-based approaches anyway. Oh, I should say, when I say a directives-based approach, what I'm talking about is just decorating your code with these kind of comments, as you might have seen with OpenMP, or we're using OpenACC here, rather than writing in a language specifically designed for the GPU. This is what I'm referring to. Another advantage of the directives-based approach is that it really is minimal interference with the source. As you can see, if you imagine you've got something like just a little loop here in your source code, you're adding a couple of lines that are just comments to the compiler unless you explicitly include them by the compiler flags. There's very little interference with the actual source itself, and this really helps with one of the main aims of the GPU port, which is separation of concerns with respect to feature development and port development. By this, what I mean is the work that we've done on the port, or the technical work, that is all really should have minimal or no impact whatsoever on anybody who's looking to develop physics within the code. So if somebody's got some great idea that they want to implement, which will add some feature to the code, they don't want to be concerned with how does the GPU port interfere with that. I can't understand all the technicalities of the GPU port. So there's that separation of concerns, and the directives-based approach certainly promotes that. Also, the CASTEP, like many other codes, is reliant on maths libraries and also MPI, and there's trivial interoperability with the directives-based approach with these things. So this is just it's not in any way an obstacle to using directives. And also, just the directives themselves, typically we find they're sufficiently well featured for most desired functionality. I'll come back to this in a little while, but for most of what we need in CASTEP, the directives are enough. We don't have to go to a low-level language specific, a vendor-specific language such as CUDA or what have you. Okay, so portability. Well, the portability almost immediately comes from the fact that you've used a directives-based approach, because by definition, using OpenACC or OpenMP, which are the only two directives-based approaches which support GPU offloading currently, these are both, as the name suggests, open source, so we should be able to use, in effect, any it should be compatible with any hardware. We're not locked into a particular vendor. Should be compatible with any compilers, again, not locked in, and compatible with any libraries. Whereas if we think about using a proprietary language, you do have that lock-in. Now, in reality, this lovely idea of this kind of utopian freedom doesn't really exist. OpenACC is currently mainly only supported by NVIDIA and Cray to some extent. OpenMP is kind of being backed by AMD, who are directly in competitors to NVIDIA. Also, Intel have got some support here, but NVIDIA have also started supporting OpenMP. So, OpenMP, when we started the project, OpenACC was by far the most mature of the two platforms. OpenMP then caught it up, but recently it looks like OpenACC is also gaining traction again. Who knows how this is going to go? We've thought about this long and hard over the years of the project. We're no closer to finding a resolution to knowing which one's going to win. The nice thing about it is, whichever one it is, it doesn't really make any difference, because the amount of work that you do with the directives is so minimally interfering with the source that even if you have to abandon one and completely translate into the other, there really isn't that much work to do. All of the development work, really, when you're using a directives-based approach, is in how judiciously you use the directives. It's not about rewriting your code. In fact, that's the exact opposite of what you're trying to do. Also, there are translation tools between these that do a decent job. But anyway, like I say, it's not really a major problem for us. So to the next slide. Yeah, okay. So I'll talk a little about performance, and performance in particular with plane wave pseudopotential DFT. As I've said before, cast step, the usual execution for cast step is in parallel in some way, usually on HPC, so large-scale parallelism. And the priority is to parallelize over K points and then over basis functions. These are just technicalities of the code, but really, if you're not familiar with materials modeling and so forth, then you can think about K points as just being sample points at which you're getting your solution, and really the equations are extremely weakly coupled with respect to K points, so you're almost embarrassingly parallel there. Parallelizing over the basis functions, which is what these little black arrows are signifying here, there's far more coupling here, and in particular with fast Fourier transforms, we get the usual 3D fast Fourier transform, parallel fast Fourier transform bottleneck that some of you may be familiar with. This would be, let's say, a typical kind of small-scale cast step run where you might have 12 processes. You've got 3 K points, so you distribute the 3 K points each to 4 processes, and then those 4 processes work in tandem to complete the calculation for that particular K point. And then at the end we get some summing over them. As I said, it's weakly coupled, so it's not really a major problem. In terms of the computational profile for each of the K points, typically what we look at are the application of the potential terms within the Hamiltonian. The local potential is FFT heavy, also loop heavy. The non-local potential is essentially just a large matrix multiplication, and then we also have diagonalization, which is also matrix multiplication bound. So, and it depends how you're scaling the code, how many processes you're distributing over, the size of your calculation and so on. At smaller scales, the FFT tends to dominate. At larger scales, the matrix multiplication tends to dominate. But in either case, there tends to be a fairly flat profile for the runtime. So plane wave DFT in this sense doesn't really lend itself to GPU porting in the way that, say, an ML application might, where you just have one large bottleneck that you can throw at the device, and if that speeds it up, then that's essentially speeding up your entire code. We have to work a bit harder with plane wave DFT. And what we typically find is this. We typically find that the memory bandwidth demands or the computational intensity over the runtime, we find it difficult to saturate the device. There simply just isn't really enough work to do per kernel to get the most out of the device. So our way of solving this, fairly obvious way, is just to oversubscribe each of the GPUs with respect to MPI processes. So if we have something like this configuration, for example, we might end up with something like this on a node where we're having multiple MPI processes on each GPU. Somewhat atypical, actually, this for plane wave DFT codes. I think most of the others are pinning just one process to the device. We found that really underutilizes the device on a typical runtime, whereas doing it this way, we tend to get more out of it. It does pose its own challenges, mind. You have to sometimes use NVIDIA, multi-processing server, and so on, so forth. But anyway, as a whole, this is our default configuration. And sorry, I'm having a little trouble with this button. Is that going to work? Yes. Okay. Yeah, and we can also alleviate some of the problems here by having dynamic runtime activation of GPU offloading. So, for example, one of our focuses is to offload the FFTs because GPUs are great at doing FFTs, but not all of the FFTs are easily offloaded. It's only worthwhile if your data is already on the device. If you're constantly having to do data transfers on and off your device, the FFT is not really going to help you. So we can get the most out of what we're doing by having some dynamic runtime control over the GPU offload as well. Okay, so what we'll look at here is one particular an exemplifier of the results that we get typically from the GPU port. These three graphs all relate to the same run, which in very crude terms is just a ground state calculation using a semi-local exchange correlation functional and using only k-point parallelism. There's no basis function parallelism going on here. This is run on a UK tier 2 GPU HPC resource. We've got about 90k points in this calculation in total. This is about 50 atoms, so a pretty small cast-step calculation. But it's as I say, it's kind of representative of what we see at various scales. So we can go to about, we can go to 90 MPI processes in total with the k-point parallelism. So that's what you can see along the bottom here. These are nodes of the HPC that we used, which is 32 cores per node and 4 GPUs per node. So we've got 8 MPI processes attached to each GPU in this configuration. And what we're looking at on the y-axis is the time per iteration, or the time per self-consistent field cycle, if you're familiar with cast-step. And you can see up here with the CPU, this is taking around, 1,100 seconds or so per iteration. This is on about half a node, so this would be about 15 processes, I think, here. And we're getting this down roughly a 6x speed up on the GPU. And then across the board, this is what we see again. We're continually keeping this speed up, which is precisely what this graph in the corner here shows. The GPU speed up across here. This is 6x pretty much all the way. It doesn't really show on this scale, but you can see it across here. And then if we look at the parallel speed up, so if the more resources we're throwing at it, how is it actually comparing to the ideal case? You can see we're kind of pretty much keeping track with the ideal line as we go up, even across the nodes, so we're getting some communication cost there, but not a great deal. And then, okay, it's veering off to something like 80% of ideal, which we think is acceptable. And in any case, this isn't really a product of the GPU port. This is just the fact that k-point parallelism is weakly coupled, so you do get there is obviously some computational cost at scale here, which is what we're seeing. So in other words, the GPU port is parallelizing well with respect to the CPU port. As I said, on these the graphs I've just shown you, these are all related to a semi-local XC functional, which is kind of the workhorse of DFT. For hybrid XC functionals, which you may be interested in if you're doing band gap calculations and the like, the algorithm used in plane wave DFT codes for hybrid XC functionals is extremely FFT heavy. It takes about 95% or more of the total runtime is spent in FFTs, which means that it's a memory bandwidth bound algorithm, essentially, which means that it's ideal for GPUs. In this case, we don't have to work hard at all for plane wave DFT. We can just essentially give the algorithm over to the GPU. The GPU just absolutely does its absolute best with the FFTs, and we can easily get something like a 10x speed up or more. And this graph just shows that we're kind of saturating the global memory throughput on the device here. This was run on Summit in the US, the HPC there before Frontier, and you can see it's like this is an easy win for plane wave DFT. Okay, so with all that in mind, one of the things that people often want to know is, okay, you can speed up my code. It's not enormously speeding up, 6 or 7 times, 6 or 7x speed up. Is it actually any use to me in terms of the finance? How much does it cost? And as a rule of thumb, we generally talk about 6 or 7 speed up is financially cost effective. Whether or not that works for your particular HPC and your particular context, of course you'd know better than me, but generally speaking that's what we find. And if we look at the example of the cast-step calculation that I just showed you, about 50 atoms and using PB-Sol or what have you as a GGA, and looking at the 32-core CPU versus 32-core CPU plus 4 V100s, we're looking at a 6x speed up in the time. And according to the UKRI guidance for Tier 2 HPC, sorry, I don't have any South Africa numbers for this, but maybe you can provide your own. A CPU hour costs around 3 pennies, and the GPU hour costs around 75 pence per hour. Okay, so if we look at what the CASTEP calculation would cost on the CPU, we're talking about £2.88, and if we look at what it would cost on the CPU plus GPU configuration, it costs around £2. So we're getting about a third saving. So around about a 6x speed up in time and around about a third saving in financial cost. Obviously, the more speed up you get, the better it's going to be. Okay, and one of the last things I'll talk about with respect to CASTEP is moving beyond the directives-based approach. We've also started to look at some hybrid porting because some of the design functionality that we want is beyond the scope of directives. These are really limited to just loops, data transfers, calling libraries. That's about all you can do, and that's about all they'll ever be able to do. They're not interested in going beyond that. Some of what we're interested in is going beyond that, however. For example, we've done some work that can benefit from CUDA inter-process communications, where we want to share device pointers across contexts on the device. So if you think about, we've got these multiple MPI processes attached, it can be a real benefit in terms of memory, avoiding memory replication if we can share pointers on the device. So we might have something like this where we keep things very generic in a high-level source model, but then as we go down to the source module, but then as underneath at the lowest levels, we can easily just use some proprietary language calls as required, something with CUDA, something with Rockham, whatever it is. But again, by encapsulating any vendor specifics in the lower level models, we're maintaining the ideas of sustainability that we talked about at the beginning. And then these compile time switches also maintain portability. If there's CUDA availability, great, then we've got this. If there's Rockham availability, we've got this. If there's nothing, then we can deal with that at the high level as well. So working things this way doesn't impact upon the cornerstones that we mentioned earlier, but it does give us functionality beyond what we can get immediately from the directives. Okay, and I'll finish off by just mentioning a couple of other codes that we've worked on under the Excalibur umbrella. The success that we've had with CASTEP, we've rolled out to a couple of other codes, OneTEP and Casino. OneTEP is a linear scaling DFT, unlike CASTEP, which is cubic scaling, and Casino is a quantum Monte Carlo code. So they're both, again, in the materials modeling way of looking at things. OneTEP's got extensive use of MPI and OpenMP, and then with OpenACC as well. And the interesting thing that they've done here is to use the OpenMP threading on the host, and then nest under that the OpenACC on the device. So that way they're trying to saturate the device as much as possible. One of the main things that they found, similar to CASTEP, FFTs are great on the device, no surprise there, but they're in contention with the data transfer, so we're having to join the dots between the hotspots in the profile. And again, similar to what I was talking about with CASTEP, even with 48 cores on an A100, they're finding that they're not actually saturating the device in terms of occupancy or memory, computational occupancy or memory. However, they are getting some nice results. So if they look at the original, their benchmark that they used here, they had something like a 30-hour runtime, which over the course of the developments that we've done over the last 9 months or year or so, we've managed to get down to something like 5, 6, 7 hours. There's still other stuff to work on in terms of what's been targeted in the profiling, but certainly these will look promising. And it's really taking exactly the same approach as I've just described. I was a consultant on both of these projects, and it's the OpenACC that's doing all the heavy lifting. Oh, well, I should say actually it's the FFT libraries that are doing the heavy lifting, but it's the OpenACC that's facilitating that from the programmer's point of view. On the casino side of things, this is slightly different because it's quantum Monte Carlo code. They can make use of some other things that we can't readily do in DFT. And in particular, they're looking at experimenting with conversion from double to single precision. For obvious reasons, on the GPU, the single precision can be a huge benefit, particularly the way the hardware has been going in recent years. It also gives you access to consumer grade cards rather than server grade, so this could be a real benefit. But they've only just started experimenting with this, but they're getting some promising results looking at this. This is relative to the CPU, so it's not having. So they've already done the conversion to single precision on the CPU, and then they're looking at how the single precision on the GPU fares again, and they're getting something like 4.5 to 5x speed up. Just in the preliminary results. This is all very small scale, but there could be room for improvement there. So I'll leave it there. I'd just like to say thank you very much to the organisers for inviting us over. We really appreciate it. It was great to see CASTEP being mentioned as well in some of the previous talks. So hopefully you find this interesting, and hopefully the GPU port will be ready for you soon. I'll leave it there. Thank you very much.
Thank you very much, Mr.